Right now, as you're trying to unwind from the day, something stranger than the news cycle is still echoing through our solar system. Long before most people started arguing about what 3I Atlas might do to Earth, it had already brushed past another world and left a measurable signature in the sky. Hours before it was a headline, Mars had already been touched, and the first world to feel it was not Earth. You didn't click on this video because you wanted drama. You clicked because the title promised something rare. What actually happened? You want a clear story you could repeat tomorrow without feeling foolish. You want to know whether this interstellar visitor truly did something to Mars, or whether the whole thing is just another round of exaggerated thumbnails and anxious speculation. Here's the short answer. Something real did happen. It was subtle, but it was measurable. Tonight, you're going to walk through it calmly, step by step. Imagine Mars during those critical hours. A cold, rust-colored planet turning under a dim pink sky. Dust devils tracing spirals across ancient riverbeds. Above them, a thin atmosphere fades into an outer layer, where atoms drift so far apart they hardly meet. That silent region is where Mars loses its air to space. Now picture a different kind of visitor drifting in from the dark. 3I Atlas, an object that did not grow up in our solar system, carrying ice and dust that formed around another star. As it rounded the sun and swept past the red planet, its invisible cloud of gas and hydrogen ballooned outward, spanning millions of miles. For a brief slice of time, that cloud overlapped with the fragile outer skin of Mars's atmosphere. While you were going about your day on Earth, instruments orbiting Mars saw something they had never seen before. A small but clear spike in hydrogen in the upper atmosphere, right where models predicted the comet's gas would pass. A spacecraft called MAVEN, built to study how Mars loses its air, suddenly found itself watching an experiment the universe had set up for free. Hydrogen from another stellar neighborhood washed over a planet that has spent billions of years bleeding its own atmosphere away. Down here, though, most people never heard that part. They were busy with the louder questions. Is Earth in danger? Is this the big one? Is something going to change on December 19th? Those questions make for great thumbnails, but they miss the most interesting line in the story. Mars has already been part of a real, documented encounter. Not a catastrophe, not a firework. A contact between two histories written under different suns. If you follow astronomy because it keeps you grounded, that detail matters. It says the universe is not just throwing rocks around at random. It is running quiet experiments in plain sight. Point the right instruments at the right place at the right time, and you can catch them in the act. Tonight, you're not here to be scared. You're here because you want the satisfaction of understanding what actually happened up there, what the geometry of the encounter looked like, how close 3I Atlas really came, what the orbiters around Mars did to prepare, and what their instruments recorded. By the end of this story, you'll know why that hydrogen spike matters, why some researchers quietly call this one of the most useful interstellar encounters we've ever recorded, and where the line really sits between sober science and wild speculation. You don't need charts or equations. You just need to lie back and follow the story in the same calm order the data arrived. First, you'll step onto Mars itself and get to know the stage. A quiet red world that seemed unchanged for billions of years. Then you'll drift into the countdown. The long nights in control rooms, when teams refined 3I Atlas's orbit and realized how improbably close it would pass. After that, you'll sit with them through the moment of closest approach, watching numbers scroll across screens as a comet from another star system briefly shares space with a planet we've been studying for decades. Just a rare, carefully documented brush between worlds. If that sounds like the kind of story you've been looking for, one that respects both your curiosity and your need to relax, you're in the right place. Take a slow breath. Let the noise of the day fall away. For the next hour and a half, you and I are going to walk through what the instruments actually saw, what 3I Atlas actually did to Mars, and why that quiet encounter may matter more than all the headlines put together. Before you can understand what brushed across Mars, you need to see the world it was drifting through, not as a map in a textbook or a snapshot from a lander, but as a living, turning, ancient body. A place that still holds the memory of rivers, even though it hasn't tasted true rainfall in billions of years. A place that whispers rather than speaks. Tonight, you're going to settle your mind directly onto that quiet world and let it unfold around you at a slow, steady pace. Imagine the thin air first. The atmosphere on Mars is barely more than a suggestion, a fragile veil of cold carbon dioxide draped over a planet that once carried water on its surface. The pressure is so low that if you stood there without a suit, moisture from your breath would freeze before it hit the ground. The sky above you would look faint and washed out, tinted in shades of orange and rose because the dust is always there, suspended, drifting, settling, lifting again. That dust shapes everything. It blows across dunes that stretch for miles, sculpting ridges into soft curves that look frozen in motion. It glides past cliffs made of layered sediment, each stripe telling the story of a time when Mars cycled through climates the way Earth cycles through seasons. Some layers mark ancient lakes, some mark volcanic ash, some mark floods that tore through the landscape when the planet was still warm enough to let water run. But that warmth is gone now. What remains is a thin breath of wind that still tries to tell the story. As you picture the dunes, imagine the valley systems branching across the planet's face. Channels so wide they rival the great river basins on Earth. Dried deltas with fan-shaped patterns etched into the ground like giant fingerprints. Deep basins that once held lakes the size of small seas. These shapes were carved over hundreds of millions of years, long before humans ever wondered whether Mars could have been a second home. If you've ever seen the images sent back by rovers, those wide, lonely panoramas where the ground looks like cracked pottery, your memory is already halfway there. But those photos only capture a moment. Tonight, you get to stretch that moment out, slow it down, and see the planet breathe at its natural pace. You can almost feel the temperature drop as the sun sinks low, casting long shadows across plains of red dust and boulder fields left behind by ancient impacts. Dust devils sweep across some regions, thin, twisting columns of air spinning silently as they gather dust from the surface. They look delicate, like they could disappear if you got too close. But dust devils can climb thousands of feet into the sky. Each one is a reminder that even dead worlds move. Even quiet worlds have weather. And some days, the entire planet is wrapped in a storm so large it can be seen from Earth. A globe-spanning haze that hides mountains and canyons under a uniform orange blur. Yet in that stillness, something else is always watching. Tiny robots, rovers the size of cars, and orbiters the size of school buses, keep their eyes on every contour of the planet. They send home postcards, not in ink, but in electrons. Images of rocky ridges, rolling dunes, swirling clouds of dust, and sunsets that fade to a deep blue because of how the atmosphere scatters light. These machines have been your eyes on Mars for decades. They've watched the passing of seasons and the subtle shifts of shadows. They've listened to the wind. They've measured the temperature of the rocks. They've done all of this silently, faithfully, day after day. And as quiet as those images look, they're not telling you the whole story. Beneath that layer of calm lies a record of violence, asteroid impacts that shook the crust, volcanic systems that once erupted with unimaginable force, floods that surged across the land, freezing instantly into stone as the atmosphere thinned. Mars is a place sculpted by extremes, a planet that still carries the memory of being alive with water, but now lives in a kind of suspended breath. This is the world 3I or Atlas approached, a world with almost no air left to defend itself, a world where atoms at the edge of the atmosphere drift into space because gravity holds them too gently. That outermost region, the exosphere, is not a surface you can touch. It is a ghostly boundary where particles are so far apart that they rarely collide. But this boundary is exactly where Mars meets the cosmos. It's where solar wind strips away the upper atmosphere. It's where radiation flies free. And it's where any visitor from beyond the solar system would make its first contact. If Earth experienced the same kind of encounter, our thick atmosphere would shrug most of it off. But Mars, having already lost most of its air, is surprisingly sensitive to the faintest cosmic touch. Even a thin cloud of hydrogen drifting across its exosphere can register as a change. Even a trace of foreign gas can appear in ultraviolet readings. The planet is so exposed that a single brush of material from a passing comet can leave a measurable signature. And that's why the story begins here. Not with Earth, not with panic, with a quiet red world turning under a thin, dusty sky, waiting unknowingly for a moment it had no control over. You've seen those postcard images from Mars, the iconic photos, the panoramic mosaics. But tonight, you're going to lay your mind directly on that landscape. You're going to feel the stillness of it, the emptiness, the fragile beauty. And then you're going to understand why scientists around the world sat up straighter when they saw 3I Atlas's trajectory crossing that outer shell of Martian air. For billions of years, this planet has turned quietly, worn down by wind and cold, untouched by anything from another star. But something was moving toward it. Something older, stranger, and carrying the chemistry of a different cosmic neighborhood. Mars didn't know it yet, but a moment of contact was coming. A moment that would leave a faint signal in the data and a faint question in the minds of the people who study it. Mars is quiet, but it is not finished. Before the world argued about what 3I Atlas might do, Before the headlines and the speculation and the worry, there was a quieter moment, one that happened long before December even entered the conversation. It happened the first time someone ran the numbers and realized the orbit didn't make sense. Not for a comet from our own system, not for anything born inside the sun's gravitational family. You can picture the moment. A researcher staring at a glowing monitor late at night, sipping a cup of coffee that went cold an hour earlier, plotting points, checking the curve of the path, watching the line bend in ways it shouldn't. At first, it looked like a normal long-period comet, eccentric, elongated, icy. But then came the recalculations, the residuals, the checks and rechecks. And slowly, the truth began to surface. This object wasn't looping around the sun. It was passing by it. Its orbit wasn't an ellipse. It was hyperbolic. That single word changes everything. Hyperbolic means unbound. It means this object wasn't thrown out from Jupiter or sent inward by the Oort cloud. It means it came from somewhere else entirely. A region with its own stars, its own dust, its own stories. Its speed alone betrayed its origin. It was moving too fast to be ours. Its incoming angle only deepened the mystery. It didn't line up with the known families of comets threading through the solar system. It was a visitor, not a resident. Once that realization landed, the next step was obvious. Predict its path. Find out where it was going. Model its arc around the sun. Estimate the gravity assist. And as the calculations grew more refined, something unexpected began to appear in the ephemerides. A close pass. Not with Earth. Not with Jupiter. Not with any of the worlds people usually worry about. It was Mars. At first, the projected distance was vague. Tens of millions of miles, then a few million, then less. As more observatories chimed in with updated tracking data, the corridor narrowed. The line on the graph tightened. The numbers sharpened. And at some point, one of the analysts must have leaned back in their chair, stared at the screen, and whispered something like, "No way. Not this close." Because what they were seeing was absurdly unlikely. Interstellar objects are rare enough. Interstellar objects passing anywhere near a planet are even rarer. But passing near a planet we actively have orbiters around, machines already in place, already equipped with sensors designed to study atmospheres and magnetic interactions. Well, that's like the universe buying a lottery ticket and handing it directly to you. Emails began to circulate. The early ones were casual, almost lighthearted. "Hey, have you seen this new solution for Atlas? It might clip Mars's sphere of influence. Then, we should probably look into this. Then, okay, this is getting interesting." But within a week or two, the tone shifted. Shorter sentences, more attachments, more charts, more urgency without panic. "We really need to organize something. Let's set up a call. Can someone confirm this with independent tracking? Is Maven configured for an event like this?" Slack channels buzzed at odd hours. Teams on opposite sides of the world scheduled telecons at whatever time zones allowed. A sense of calm urgency settled in. Not fear, never fear, but the quiet recognition that history might be about to drop an opportunity into their hands. An opportunity that wouldn't come back. No one was worried about a collision. The geometry ruled that out early. The object would pass too far away for impacts, too fast for any gravitational entanglement. But the worry wasn't about danger. It was about missing something, missing a chance for instruments to see what happens when a world with barely any atmosphere interacts with gas from another star system, missing a natural experiment that would never repeat in their careers. The countdown began without anyone announcing it formally. Weeks out, mission planners watched the numbers drift. They recentered their models. They checked the uncertainties. Some nights, the closest approach distance shrank by a few thousand miles. Other nights, it grew. But always, it stayed close. Too close to ignore. Days before the flyby, the activity intensified. Calibration checks, instrument rotations, updates to pointing schedules. MAVEN, Mars Express, the Trace Gas Orbiter, all of them adjusting their plans. Tiny mechanical hearts beating quietly in orbit around a world that could not understand what was coming. Inside mission control rooms, the lighting stayed dim, the screens stayed bright, and the room temperature always felt a few degrees too cold. Engineers stared at strings of numbers scrolling across displays. Flight dynamics teams reran simulations every few hours. The object's position updates came in like steady ticks of a cosmic clock. Each tick pulled it closer to Mars. Hours before closest approach, there was nothing left to adjust, nothing left to change. Every plan had been written, reviewed, approved. Every instrument that could record something was pointed at the thin envelope of air above Mars. Every spacecraft orbiting the planet had been slotted into position, and every person involved knew something simple. There was no rewind button on the universe. If they missed this alignment, this exact geometry of Mars, the Sun, and an interstellar visitor, they would never get another. The red planet kept turning slowly under its dusty sky, unaware of any countdown. But in labs and offices around the world, you could feel the tension settle. Not sharp, not frightening, but heavy with meaning. The kind of tension that tells you something rare is about to happen. The kind of tension you only get when you realize you're about to witness a meeting between worlds that have never crossed paths before. Step by step, minute by minute, the final approach tightened. The trajectory was locked in. The closest distance was confirmed. And suddenly, there were no more maybe calculations. No more uncertainties. Only the quiet truth. 3's Eye Atlas was going to sweep past Mars at a distance so close it defied probability. If you've ever wondered how humans prepare for a moment like that, a moment written in celestial mechanics long before we were here to notice it, now you know. You're about to sit in on a once-in-history rehearsal for the next interstellar visitor. And so, the countdown reached 0, and Mars found itself sharing a moment in space with a stranger from another star. If you slow the universe down to the pace of a breath, if you take the clockwork of the solar system and let it move frame by frame, you can begin to understand how extraordinary this moment really was. Not dramatic, not explosive, nothing that would shake a planet or light up its sky. Just two paths, two long ancient trajectories, intersecting in the quiet dark. For a few hours, 3 Eye Atlas and Mars occupied the same cosmic neighborhood, close enough to share the same thin ribbon of space. Close enough that their stories briefly overlapped. Imagine pulling the camera back until you're hovering above the plane of the solar system. Below you, the planets trace their orbits like glowing threads. Mars is a small red bead following its steady path. Far out on a long inbound arc, 3I Atlas swings in toward the sun, its hyperbolic path slicing through the planes of the planets at a steep angle. On a screen, you would see two dots drifting toward each other with impossible precision. Mars on one thread, 3I Atlas on another, until suddenly, without fanfare, they're side by side. To the computers tracking the event, it looked like geometry. Distances shrinking, numbers converging. But if you could step back and look with your eyes instead of equations, you'd see something almost poetic. The long, translucent tail of an interstellar visitor sweeping across the region of space Mars was about to pass through. Not touching Mars directly, not colliding, but leaving a faint trail of gas and dust along the planet's path. A brushstroke painted millions of miles wide, but only a few molecules deep. Now imagine you are actually there, standing on the dusty surface of Mars, the ground cold beneath you, the sky tinged with soft orange light. The air is thin and sharp, the kind that whispers rather than moves. You tilt your head back, and against that pale sky, you see something unusual. Not a bright comet with a blazing core, just a faint, slowly moving haze, almost invisible unless you stare long enough. A smudge stretching across the sky, almost like an eyelash drifting past the sun. No human eyes were there to witness it, of course. Only machines. Tiny rovers still working through their daily routines. Orbital instruments watching from above. But if a person could have looked up in that moment, they would have seen the most delicate kind of cosmic encounter. A silent shape moving against a silent sky. Something foreign, passing through a world that has been waiting billions of years for a visitor like this. That is what scientists mean when they call it a cosmic handshake. It isn't a collision. It isn't a strike or a shock. It's the universe letting two stories touch each other for a moment. One world formed around a young sun. One icy traveler forged under a different star entirely. And for a few hours, their paths overlapped so precisely that even the most conservative mission planners had to stop and stare. From a mathematical standpoint, the odds were almost absurd. Interstellar objects aren't just rare. They spend most of their lives in the empty distances between stars, where the chances of crossing a planet's orbit are microscopic. But this one didn't just cross an orbit. It crossed the orbit of a planet with functioning satellites, active sensors, and instruments specifically designed to measure the very thing 3I Atlas was shedding. Gases, ionized particles, and the faint outlines of a comet's coma. For years, Mars has been losing its atmosphere to space. Solar wind strips particles away. Ultraviolet light cracks molecules apart. The planet is fragile, its exosphere thinning like breath on glass. And into that vulnerability drifted a cloud of hydrogen, carbon-based dust, and faint traces of organic material that formed under another star. A stranger from the edge of nowhere. A visitor that spent millions of years in interstellar darkness before gliding into our system. During closest approach, the distance between Atlas and Mars shrank to the kind of number you only see in textbooks or simulations. If you enlarge the solar system to the size of the United States, this encounter would be like 2 grains of sand floating past each other within a few inches. And yet, on an atomic level, in the delicate upper layers of Mars' exosphere, that was close enough. Close enough for hydrogen atoms to drift. close enough for ultraviolet sensors to register a shift, close enough for a moment of contact without impact. If you freeze time in that instant, pull the universe to a stop, and look down on the scene, you see two travelers passing each other like ships in an endless night. Mars, tired and weathered, carrying every scar from its past, and Atlas, bright and fraying at the edges from its recent pass around the sun. It wasn't a collision. It was a conversation at the edge of Mars's sky. A conversation measured not in words, but in particles. Not in sound, but in resonance. For a planet as quiet as Mars, even the faintest whisper is meaningful. And that's what makes this moment so awe-inspiring. A few hours. Just enough time for the planet to spin beneath a visitor's passing cloud. Just enough time for a handful of atoms to drift downward through the exosphere. Just enough time for sensors to blink with readings that made scientists lean forward in their chairs. What exactly passed over Mars during that handshake? Did hydrogen from 3I Atlas skim the outer atmosphere? Did ultrafine dust from another star brush across a world that once held oceans? Did molecules that formed 10 light years away drift into a planet that hasn't known warmth in billions of years? The encounter is over now. Mars keeps turning. Atlas keeps racing outward, fading into the distance. But the data remains, waiting to be decoded. And you're about to walk through that decoding piece by piece. To understand what was said in that silent conversation, we have to look at who these two partners really are. To understand why this encounter mattered, why scientists still replay those hours again and again, you need to step back from Mars, back from 3I Atlas, and look at the universe through a wider lens. Not the lens of orbits and datasets, but the lens of origins. Because what happened near Mars was not just a passing of two objects. It was the meeting of two stellar family trees that have never crossed before. Two different birthplaces, two different pasts, two different chapters of the cosmos opening on the same page for the first time. Everything in the solar system, including you and everything you've ever known, shares the same ancestral signature. Our sun formed from a collapsing cloud of dust and gas more than 4.5 billion years ago. The planets took shape from that same cloud, spinning disks of material slowly cooling and condensing. The rocks you walk on, the iron in your blood, the dust on your bookshelf, all of it carries the same chemical handwriting, the same birth certificate, the same cosmic surname. Mars carries that signature too. Its rocks, its dust, its frozen minerals, they all formed in the same nursery that gave rise to Earth. They all grew up under the same star. They are local, familiar, part of our family. But 3I Atlas is not. Its ices were born around another star entirely, a place with its own cycles of heat and cold, its own chemistry, its own radiation patterns, its own storms. A place whose identity is written into the ratios of isotopes frozen inside the comet's nucleus. A place with a history we don't know, carved into molecules we've never touched. Its dust grains carry the fingerprints of a different cradle. Its organics, simple chains of carbon and hydrogen, carry the flavor of light years traveled. Its entire body is a time capsule from somewhere so distant it may not even exist anymore. That is what makes this moment near Mars so remarkable. For a brief period, the child of our sun and the child of another star shared a space small enough for their materials to mingle. It wasn't dramatic. It wasn't loud. But from a scientific perspective, it was profound. When two stellar histories collide, even gently, meaning is exchanged. Even one atom from another star makes Mars a little less local. Picture the scene again. Mars turning slowly, its thin exosphere stretched out like a barely there halo. Into that halo drifts hydrogen, dust, and microscopic fragments of ice released from 3I Atlas as it shed material after its pass around the Sun. The physics is simple, but beautiful. Mars has almost no magnetic field left, barely any protection. Its exosphere is open, porous, a place where particles can slip through without bouncing. And for a short time, particles from another star had the chance to do exactly that. It's like two family trees crossing for the first time in billions of years. Most branches will grow in parallel forever. Most histories will never touch. But every once in a while, the universe allows two separate stories to graze one another, and something new becomes possible. You might wonder how much of that other star's story could really stick to Mars. Could a few hydrogen atoms matter? Could a few molecules drifting through space change anything? On a geological scale, no. On the level of continents or canyons or weather patterns, no. But on the level of meaning, on the level of chemistry, origin, and cosmic context, yes, absolutely. Our understanding of a planet isn't built only from mountains and dust storms. It's built from the atoms we find, the ratios they hold, the slight variations that tell us where they've been. Scientists study atmospheres one particle at a time because the smallest changes often reveal the largest truths. And that's why this moment matters. We cannot count each atom. We cannot track them one by one. But we know the physics. We know the overlap. And we know that during that overlap, Mars was touched by something not from here. Something that was never part of our Sun's story. For billions of years, Mars has belonged entirely to our solar system. Every grain of dust, every rock, every frozen lake bed, all local, all homegrown. But after the encounter with 3I Atlas, even if the change was microscopic, it was still real. From this moment on, Mars is no longer purely a child of our Sun. Somewhere in its sky, in its outermost layers, there now floats a trace of another star, a chemical whisper from a different corner of the galaxy. And in that whisper is a reminder. We are not alone in the story of cosmic origins. Worlds can meet. Histories can overlap. Material can wander between stars long after the stars themselves fade. You and I are used to thinking of the solar system as an isolated neighborhood, but in truth, it is porous. It leaks. It receives. It exchanges. Every so often, the universe sends something across the void to remind us that nothing stays entirely separate forever. When you think about it from your place on Earth, lying back, listening, letting your thoughts slow down, it becomes easy to see yourself in the story. You are built from stardust too, from elements that once drifted freely through space. You are the product of collisions, accretions, fusions, and quiet transfers of material. On human scales, we meet each other. On cosmic scales, stars do the same. And Mars, for a short moment, played host to one such meeting. We may never know the exact number of atoms exchanged. We may never see the molecules themselves. But we know what principles govern that moment. We know the physics. And we know that even the faintest interaction between two stellar histories carries meaning. Scientific, philosophical, and personal. Even one atom from another star makes Mars a little less local, but no atom tells its story alone. It takes a planet of instruments and a planet full of people to listen. Long before the data began to flow in, long before the world had any idea that Mars was about to share a moment with an interstellar visitor, there was something far less glamorous unfolding behind the scenes. A global scramble. Not the kind you see in movies. No alarms, no shouting, no dramatic countdowns. This was the quieter kind. The kind built from half-asleep emails, awkward time zone calls, overbooked calendars, and the relentless truth that the universe refuses to wait for human bureaucracy. If you've ever worked in a system where timing matters but the paperwork moves like molasses, you'll recognize the feeling instantly. The first messages came in casually enough. JPL scientists sending quick updates to their counterparts at ESA. Someone on the Maven team asking a friendly question in a shared channel. Someone in Europe double-checking the new orbital calculations. A researcher in Beijing forwarding a simulation that matched the updated trajectory. It looked like routine collaboration at first, exactly the kind of cross-agency chatter that happens every day. But then the numbers tightened. The closest approach shrank. The uncertainty dropped. And suddenly, the tone changed. Those early casual notes turned into late-night emails marked urgent. Slack messages popped up with words like confirm and verify. Quick calls turned into mandatory telecons. ESA analysts sent spreadsheets with color-coded timing windows. CNSA teams forwarded instrument constraints from their orbiter. Someone at NASA wrote, "We really need to coordinate on this." And someone else immediately replied with, "Let's get everyone on a call today." Then reality hit. NASA was in the middle of a partial shutdown. Not a full one, just enough to complicate everything. Budgets were frozen. Travel was restricted. Overtime hours were tightly capped. Certain offices were half empty. Some staff were officially furloughed, which meant they weren't supposed to be working at all. But science doesn't pause itself just because a government office does. And Mars certainly wasn't going to drift a little slower while NASA sorted out funding debates. For the teams watching the approach trajectory, the frustration was quiet but real. They had the math. They had the instruments in orbit. They had the curiosity. What they didn't have was time. Every hour lost to bureaucracy was an hour the universe did not care about. As one mission coordinator put it, space doesn't care about our shutdowns or our calendars. The sky runs on its own clock. So NASA did what NASA has done for decades. It adapted. Senior engineers volunteered extra hours. Younger researchers logged in from home computers. Managers approved exceptions wherever they could. Teams restructured their schedules so that furloughed specialists could join calls as informal consultants, a gray area workaround that everyone pretended not to notice, but everyone depended on. ESA stepped in with an elegance only Europe can manage. Their teams offered to handle chunks of the planning timeline. They shared code, orbital tools, and simulation outputs. They sent over high-resolution models of the expected dust environment near Mars. They double-checked the geometry of the pass. A mission planner in Germany even generated a full pointing schedule for Maven, just in case NASA couldn't get internal approval on time. CNSA added another layer of support. China's Tianwen-1 orbiter was already around Mars, equipped with sensors NASA didn't have. Chinese researchers offered to coordinate their observation windows with MAVEN and Mars Express. During one late-night call, someone at JPL joked that this was the most informal multilateral science treaty ever written. And someone at ESA replied, "Yes, but it works better than the formal ones." Together, they built a patchwork plan held together by shared curiosity rather than perfect funding. It wasn't seamless. It wasn't efficient. But it was enough. The universe had thrown them a rare event, and they were determined not to waste it. The closer the date came, the more intense the coordination grew. Schedules circulated with timestamps in 3 time zones. Slack channels lit up at odd hours. Messages came in with lines like, "Confirm exosphere density assumptions," "Upload final ephemeris," and "Need verification from Beijing before we lock this in." It was a strange kind of pressure. Not fear, not danger. Just the weight of rarity. This wasn't something that would happen again next month, or next year, or even in most of the lifetimes of the people working on it. This was a once-in-history alignment, an interstellar object passing close enough to a planet with orbiters to record it. Missing it wasn't an option anyone wanted to accept. People who had never spoken before were suddenly working side by side. Agencies that usually navigated political friction were now syncing spreadsheets and adjusting timelines together. Every scientist involved knew that when moments like this come, you show up. And somehow, despite budget freezes, partial shutdowns, time zone chaos, and the usual red tape of 3 different space agencies, they made it work. ESA, NASA, and CNSA reached a quiet consensus. The pointing schedules were approved. The observation windows were reserved. The instrument settings were finalized. Every spacecraft around Mars had its task. Every team had its timing. They were ready. Human systems had creaked and complained, but science, real science, had pushed through. They didn't just get the observations. They didn't just coordinate. They showed up for Mars. They showed up for the universe. And they showed up for each other, because curiosity is a stronger force than bureaucracy. With the emails sent and the plans locked in, it was time to aim the cameras already circling the red planet. By the time the plans were finalized, Mars was no longer just a lonely world spinning under a thin sky. It had become the stage for a choreography so delicate, so precise, that every spacecraft orbiting it might as well have been a dancer performing a once-in-a-lifetime routine. Engineers often joke that orbiters move with the grace of bricks. But during events like this, when every second matters, those bricks become ballerinas. And the people guiding them become something like conductors, coaxing beauty out of metal and mathematics. 3 spacecraft took the lead: ESA's Mars Express, NASA's MAVEN, and NASA's Mars Reconnaissance Orbiter. Each one old in spacecraft years, each one carrying scars from past maneuvers, glitches, safe mode events, and the thousands of lines of code patched into them over the course of their lives. They were stable, reliable, but not flexible. Any change had to be handled with the gentlest touch. Mars Express follows a long, looping orbit that swings it far out into space before diving close again. It's perfect for wide-angle observations, for catching the big picture. MAVEN circles lower, skimming close to the upper atmosphere, studying how Mars loses its air. It's sensitive, finely tuned, and capable of noticing the faintest shift in particles. MRO is the powerhouse. Sharp instruments, high-resolution imaging, and deep experience watching transient events. Together, they formed a triangle of watchers around the red planet. 3 perspectives, 3 sets of tools, 3 ways to catch whatever 3-eye atlas left behind. But none of these spacecraft were designed to flex quickly. Their observation schedules are planned weeks ahead. Their memory is limited. Their fuel is precious. Their attitude control systems can only handle so much bending before they risk overheating or drifting off alignment. And yet, with days left before the encounter, engineers around the world were rewriting command sequences line by line. Imagine that room. Dim console lights reflecting off tired faces. A half-empty coffee on one desk. Someone muttering numbers under their breath while staring at a simulation running on 3 monitors. Another engineer calculating the thermal load of rotating an instrument 10 degrees off its nominal position. Someone else running a test to make sure a proposed pointing maneuver wouldn't trip the spacecraft's emergency protocols. Every change required 3 or 4 checks. Every check required someone to stay late or wake up early or dial into a call that started at 3 a.m. in their time zone. A single typo in the uplink code could send a spacecraft into safe mode. A single incorrect timestamp could cause the instrument to look the wrong direction at the critical moment. They had one chance, one window, one alignment of orbit and visitor and light. And so, they choreographed it carefully. As one flight dynamics engineer put it, we were choreographing a ballet in a gravity well, with the universe as our only audience. Mars Express would rotate its instruments outward, toward the region where the comet's cloud was expected to pass. Its orbit would give it a sweeping vantage point, a chance to see the tail not as a thin line, but as a broad influence in space. Maven would time its closest passes perfectly, dipping into the exosphere right when the hydrogen density was predicted to shift. MRO would scan the illuminated edge of Mars's atmosphere, looking for the faintest UV scattering from foreign particles. But that was only the space-based side of the ballet. On Earth, a different choreography unfolded. In Chile, high in the Atacama Desert, telescopes were placed on continuous monitoring cycles. Every few minutes, they snapped images that would later be stitched together into a time-lapse of the approach. In Hawaii, above the clouds of Mauna Kea, photometric measurements were taken to search for subtle brightening or dimming of the comet's coma. In Australia, observers captured spectra during the hours when Mars dipped into the southern sky. These observatories formed a relay, handing the baton from one night sky to another as the Earth rotated. When the sky brightened in Chile, it darkened in Australia. When Hawaii lost Mars to the horizon, Chile picked it up again. And then there were the amateurs, the backyard astronomers with their personal telescopes, careful tracking systems, and extraordinary persistence. Some of the most continuous coverage came from them. Tiny observatories built in garages, on rooftops, at the edges of towns lit by street lamps. They provided photometry that filled gaps no national agency could cover. They shared images in real time with researchers continents away. Some caught details professionals missed simply because they were pointing at the sky when no other telescope happened to be. Together, it all formed a network, a global mesh of eyes focused on a single moment near a single world. A mesh created out of curiosity rather than funding, dedication rather than orders. Meanwhile, the orbiters continued their dance. The commands had been uploaded, the pointing angles locked in, the instruments warmed, the thermal models accepted. The spacecraft began slow rotations, aligning their sensors with the patch of sky where 3i Atlas would thread past Mars. At a certain point, the teams reached what everyone quietly calls the point of no turning back. Once the uplink commands were executed, nothing more could be changed. The spacecraft were committed. Engineers leaned back in their chairs. Some closed their eyes. Some stared at the ceiling. Some stepped outside to breathe. They had done everything they could. Every angle calculated, every instrument prepared, every contingency checked. Now, all they could do was wait. Waiting is one of the most underrated aspects of spaceflight. It's not glamorous. It's not dramatic. It's long, slow, and entirely out of human control. The spacecraft circle. The planet spins. The visitor passes by. And the data, eventually, begins its long journey home. And then, after the quietest, longest wait, the first packets of light began to fall back toward Earth. When the orbiters finished their ballet and the ground telescopes finished their relay, the world entered a different kind of silence. The silence of waiting for light to travel millions of miles back home. Data never arrives all at once. It slips in quietly, packet by packet, like tiny envelopes drifting down a long cosmic mail route. And in those first minutes after closest approach, no one knew whether all the effort had captured anything at all. The first packets from Mars Express came in as raw frames. Noisy, grainy, full of bright streaks and dark patches. Most people never see raw space data. It's messy, imperfect, more like a smudged sketch than a photograph. Engineers stared at the jagged patterns of pixels, knowing that somewhere inside those blotches was the truth of what had passed near Mars hours earlier. When you hold raw data up to the light, it doesn't whisper its story right away. It has to be coaxed, cleaned, corrected. The noise filtered out, the stars removed, the scattered sunlight subtracted. And so the teams got to work, at consoles, in labs, in offices still smelling of stale coffee. They ran calibration scripts. They matched the frames against star catalogs. They adjusted for instrument drift. Slowly, fuzziness became shape. Shape became structure. Structure became a faint glowing smear across black space. Then the coma emerged, subtle but unmistakable. What had looked like noise resolved into a cloud, broad, translucent, gently curved around the trajectory of 3i Atlas. Not bright, not solid, but visible. A halo of dust and gas released from a body born under a different star. Data from MRO added definition. The coma was wide, asymmetrical, fanned out from solar heating. Part of it stretched in the direction Mars had just rotated under, like a thin breath exhaled into space. Hours later, the tail appeared in processed frames. A single line at first, then a long, diffuse streak extending away from the sun. Compared to comets from our own system, it looked different. Less organized, less sharp-edged, more like a drifting plume than a sculpted beam. It carried age, distance, history, the signature of an object that had wandered between stars long before Earth learned to form oceans. On another console, Maven's UV spectrometer returned its first files. These looked nothing like images. more like rows of numbers, strips of wavelength intensities plotted across time. Maven lives close to the edge of Mars's atmosphere, dipping in and out of the region where the exosphere becomes space. And during the hours surrounding the flyby, its ultraviolet instrument was set to monitor one specific thing: hydrogen. Hydrogen is the lightest element in the universe. It escapes easily. It reacts quickly. It dissolves into solar wind like smoke into air. And because Mars has lost so much of its atmosphere already, hydrogen around the planet fluctuates with seasonal patterns, solar cycles, and thermal tides. Everything about it has to be interpreted carefully. Which is why, when the first processed UV plot rendered on screen, the room went still. In the graph, Mars's baseline hydrogen levels formed a quiet, predictable line, steady, with subtle ripples. But at the exact window of closest approach, at the exact arc Maven had been instructed to watch, the line bent upward. Not wildly, not dramatically, but unmistakably. A jump. A clean, measurable increase. Exactly when 3I Atlas's cloud was predicted to overlap with the upper atmosphere. Exactly when the cosmic handshake occurred. When the curve jumped, the room went completely silent. That silence said everything. That's how Dr. Maya Chen, one of the data analysts reviewing the files, described it. It wasn't the kind of moment you see in movies. No cheering, no shouting. Just people leaning closer, blinking slowly, reviewing timestamps, and confirming what their eyes were telling them. Something in that cloud had washed across Mars. Something that wasn't there before. Something that matched the timing, the direction, and the expected signature of interstellar hydrogen. To understand why this mattered, imagine how scientists think. They don't trust coincidence. They test it. They subtract background noise. They check whether solar wind conditions could cause a similar spike. They compare Mars Express data. They overlay Maven's orbit with the trajectory of the comet. They look at the phase angle, the heliocentric distance, the vacuum temperature. And when everything still points to the same conclusion, they begin to allow themselves a feeling they don't often indulge: quiet satisfaction. Layer by layer, the evidence stacked up. Mars Express confirmed the presence of diffuse material along its line of sight. MRO captured faint scattering in the UV band. Ground-based telescopes recorded a subtle widening in the comet's coma right before the flyby. And Maven, closest to the edge of Mars's atmosphere, saw the hydrogen rise exactly when the models predicted it would. At this point, one question hung over the room with gentle insistence. How do we know this hydrogen isn't just Mars itself? And it was a fair question. Mars releases hydrogen naturally, especially during warmer seasons. But the timing was wrong for seasonal peaks. The location was wrong for atmospheric tides, and the magnitude matched predictions made specifically for interstellar material drifting across the exosphere. This wasn't noise. This wasn't coincidence. This wasn't normal Martian behavior. It was a signature, a tiny one, a quiet one, but a real one. For everyone who had spent weeks preparing the spacecraft, rewriting the pointing commands, coordinating across continents, and waiting through hours of silence. This was the moment of payoff. The universe had whispered back. Something foreign had touched a world that has not received anything new in billions of years. And even though the data was still rough, still incomplete, still waiting for deeper analysis, the truth was clear enough for anyone in that room to feel it in their chest. Mars had been brushed by a visitor from another star. To understand what those numbers really mean, we have to look at the thin, ghostly skin of air wrapped around Mars. To understand what really happened to Mars during those quiet hours, you have to picture the planet's atmosphere not as a thick, comforting blanket like Earth's, but as something closer to breath on a cold window. Delicate, sparse, and almost transparent. Mars once had an atmosphere dense enough to hold rivers and lakes, but that time is long gone. Today, only the faintest shell of gas remains, thinning rapidly as you rise upward, until eventually you reach a place where the atmosphere stops behaving like air at all. That place is the exosphere, the boundary between Mars and the rest of the universe. It's not a surface. It's not a layer you could stand on. It's a region where molecules are so far apart that they rarely collide. A realm where particles drift freely, guided more by gravity and sunlight than by winds or weather. If you could float there, above the tops of the tallest Martian mountains, you wouldn't feel anything on your skin. You would simply be suspended in a silence so complete it would feel like a form of pressure. Mars's exosphere is mostly hydrogen, not thick clouds of it, just a thin haze, a whisper of atoms stretching tens of thousands of miles outward. These hydrogen atoms are constantly escaping into space, evaporating from Mars the way steam drifts upward from a cup of cooling tea. It's a fragile, ghost-like glow, invisible to your eyes, but clear to instruments tuned to ultraviolet light. Now imagine something else approaching that ghostly veil. An interstellar visitor carrying its own cloud of hydrogen. When comets, whether local or interstellar, swing near a star, their surface ice warms and begins to sublimate. Molecules split apart. Water becomes hydrogen and oxygen. Carbon chains fragment. Dust grains lift off like pollen caught in a breeze. Around every comet, this process creates a vast, invisible shroud called the hydrogen corona, a loose, expanding sphere of hydrogen atoms blown outward by sunlight. Around 3I Atlas, that corona stretched millions of miles. It wasn't bright. It wasn't dangerous. But it was enormous, so large that long before the comet's core came anywhere near Mars, its hydrogen was already flowing ahead of it. If you want a visual, imagine Mars's exosphere as a thin mist rising off a quiet lake at dawn. And now imagine a passing breeze drifting across that mist. Not strong enough to churn the water, not concentrated enough to disturb the surface, but enough to let the two layers touch. That is what happened when 3I Atlas arrived. Two invisible veils brushing against each other in slow motion. When that hydrogen corona swept across the edge of Mars's exosphere, a few simple but profound things happened. Hydrogen from the comet mixed, ever so slightly, with hydrogen already evaporating from Mars. Some atoms continued drifting outward, carried away by solar wind. Some ricocheted deeper into the exosphere, lingering longer than models predicted. A small number likely interacted with oxygen atoms in the thin upper atmosphere, creating momentary flashes of excited particles visible only in the ultraviolet spectrum. Others may have drifted downward by a fraction of a mile before escaping again. These are small events, tiny on the scale of planets, enormous on the scale of meaning. The physics is elegant. No collisions you could see, no shock waves, No glowing streaks or dramatic flares. Just atomic interactions governed by laws older than the sun. Mars whispered outward, Atlas whispered inward, and for a handful of hours, those whispers overlapped. Think of Mars's exosphere as a whisper, and 3I Atlas as another whisper passing through it, said Dr. Anil Das, a space physicist who has spent years studying planetary atmospheres. And that is exactly what the hydrogen data shows. A soft, brief harmony between two sources of gas that normally would never meet. You might wonder how long those interstellar guests stay. Hydrogen doesn't linger anywhere for long. Not on Mars, not in the solar wind, not in interstellar space. Most of it escapes quickly, slipping away from Mars's weak gravity and fading into the larger flow of particles streaming toward the edge of the solar system. But that isn't the end of the story. Some atoms collide just gently enough to slow their escape. Some mingle at the boundary layer where Mars's atmosphere fades into space, altering densities in ways instruments can detect. A few drift deeper into the exosphere for hours or days before ultraviolet light strips them of energy and sends them outward again. Most of them leave, but not all at once, not immediately, and not without leaving a trace in the data, a fingerprint of timing and movement that matches the passage of 3I Atlas. And here is where the story becomes even more interesting. Hydrogen is only the lightest and most abundant component of the comet's corona. It is the easiest to detect, but the least informative. The real intrigue comes from what else was carried within that cloud: oxygen from broken water molecules, carbon from ancient organics, fine dust grains formed around a different star. Mars's exosphere is so thin, so vulnerable, that even a small number of these foreign atoms matter, not in a geological sense, but in a story of origin sense. For billions of years, nothing from outside our solar system has reached Mars in measurable amounts. But during the hours when 3I Atlas brushed past, the exosphere recorded a change. Not dramatic, not transformative, but undeniably real. This is how the universe exchanges stories, not through loud collisions, but through particles drifting quietly from one history into another. A hydrogen atom born around a distant star can travel millions of years through cold darkness, glide past the sun, and for a single moment touch the edge of a world that once held oceans, and then drift away again, its journey continuing. The beauty of this event isn't in how much material was exchanged, but in the fact that the exchange happened at all. Mars tasted the outskirts of another star's chemistry. That moment may be small, but it is legitimate. It is measurable. And it is something no planet in our solar system has experienced in recorded history. But hydrogen is only part of the story. The real intrigue lies in what else 3I Atlas was carrying. By the time scientists finished staring at the hydrogen data, their attention began to shift to something far more subtle and far more tantalizing. The chemistry hidden inside the faint light reflected off 3I Atlas. Hydrogen is easy to detect. It shouts in ultraviolet. But the heavier molecules, the ones that whisper in longer wavelengths, require patience. They need clean spectra, careful calibration, and a willingness to sit with lines and curves that look like nothing more than gentle hills on a graph unless you know how to read them. Spectroscopy is the closest thing astronomy has to fingerprinting. Every molecule absorbs and emits light in its own style, unique dips and peaks at specific wavelengths. To the untrained eye, A spectrum looks like a wriggling line drifting across a computer screen. But to an astrochemist, that line is a conversation. It's a record of which molecules were present, how they behaved, how they interacted with sunlight. It reveals not just what something is made of, but how old it might be, how warm it was, even the environment it came from. And when the teams began to pull spectra from the coma of 3I Atlas, cleaned, corrected, scrubbed of noise, they noticed something familiar and unfamiliar at the same time. Carbon monoxide, carbon dioxide, methane, the usual suspects that show up in nearly every comet. But then came the faint signatures of something more elaborate. Long-chain hydrocarbons, fragments of carbon rings, possible precursors to amino acids, nucleobases, and other molecules that sit at the foundation of biology. No one jumped to conclusions. They never do. Spectral lines are interpreted carefully, slowly, sometimes agonizingly. But as more data rolled in from MRO's detectors and ground-based infrared spectrographs, the pattern solidified. There were organics in the cloud around 3I Atlas. Not simple ones, not trivial ones, but bona fide complex organics created either in its parent star system or in the interstellar medium during its long journey. This didn't mean life. It didn't imply biology, but it did imply something profound. Chemistry in the universe is generous. It produces the building blocks of life wherever it can. It spreads them across space with no concern for borders, planets, or star families. Life is picky, but chemistry is generous, said Dr. Sophia Marin, an astrochemist who has spent decades studying organic signatures in comets. And 3I Atlas proved her right. Even a visitor from another star carries the same kinds of fundamental molecules we've found around local comets, meteorites, and dust clouds. In a way, it humbles you. The idea that molecules essential to life on Earth, carbon chains, nitrogen-bearing organics, fragile molecular fragments, are not confined to our solar system, but are instead widespread, produced naturally by cosmic conditions common across the galaxy. When 3I Atlas passed Mars, some of these organics were almost certainly lifted into its coma and drifted into the hydrogen cloud that swept across the planet's outermost air. Not in large quantities, not enough to change anything geologically, but enough that a handful of molecules, carbon-based, starborn, older than Earth, passed within touching distance of a world that once had its own rivers and lakes. That thought alone is enough to make almost anyone stop and breathe a little slower. Could similar visitors have dusted Earth in the deep past? Could interstellar comets have delivered organic ingredients to our oceans long before life began here? It's not a new question, but encounters like this breathe fresh life into it. They don't prove anything. They don't confirm panspermia, but they whisper the possibility that the seeds of biochemistry might travel farther and more often than we realize. Imagine the long journey of a single molecule, born near a young star, frozen into an icy comet, broken free by sunlight, drifting across planets, and finally brushing against the exosphere of Mars. Imagine how many such molecules exist in the galaxy right now. The universe doesn't hoard complexity. It distributes it widely, quietly, persistently. And that is what makes the chemical data from 3I Atlas so meaningful. Even though no instrument on Mars could directly catch these organics, we know they were there, carried in the tail and coma. We know that for a brief moment, their paths intersected with Mars. And we know that the chemistry composing the building blocks of life is not unique to us. It is part of the universe's default vocabulary. This doesn't make Mars alive. It doesn't make 3I Atlas a messenger of biology. But it does make both of them participants in a story far older and far bigger than our solar system. The story of matter learning to arrange itself into forms that, under the right conditions, can eventually ask questions. And that is why the organics in 3I Atlas matter. They are evidence not of life, but of potential. Raw, unshaped, cosmic potential. They remind us that Earth is not special because it has organic molecules. Earth is special because it had the environment to do something remarkable with them. But those molecules themselves, they are everywhere. So after all this effort, all this chemistry, we're left with a deceptively simple question. Did Mars change forever? When you hear a question as large as, did Mars change forever? Your mind may jump to images of dramatic transformation, a reddened world suddenly glowing blue, or a comet striking hard enough to carve a new canyon. But real change, especially in astronomy, is rarely dramatic. It is quiet, subtle, more like the slow shift of a shadow than the fall of a hammer. To answer the question honestly, you have to look through two different lenses: the strict, hard numbers only lens of physics, and the wider, more reflective lens of meaning. Both tell the truth. They just tell different versions of it. Through the first lens, the one preferred by cautious dynamicists and planetary scientists, Mars did not change in any way you could see with the naked eye. The mass of material added by 3I Atlas was tiny, microscopic, almost philosophical in scale. Most of the hydrogen that washed across the exosphere escaped back into space within hours or days. The carbon fragments and dust grains that drifted near the planet were too few, too scattered, and too light to make any geological imprint. If you asked a strict physicist whether Mars changed, they might shrug gently and say, not in a way that affects mountains, valleys, temperatures, or seasons. They would tell you that you cannot walk onto the surface of Mars and point at any rock and say, this atom came from 3I Atlas. They would remind you that everything we're talking about operates at a scale smaller than a breath, smaller than a whisper, smaller than a grain of dust. And they would be right. But through the second lens, the one that asks what it means for two stellar histories to meet, Mars absolutely changed. You could think of it this way. For 4.5 billion years, everything on Mars belonged to the same family tree as everything on Earth. Same star, same collapsing nebula, same cosmic birthplace. Mars was, in chemical terms, purely solar. Every atom, every layer, every grain of its soil. Then, for a few hours, something foreign drifted through that purity. Something older than the sun, older than our planets, older than every riverbed and canyon etched into Martian stone. And some of it stayed, even if just for a moment. Take one hydrogen atom, just one. If it slowed down enough, if it drifted a little deeper into the exosphere, if it lingered longer than expected, that singular atom now belongs to Mars. Not as a metaphor, but as a matter of fact. And from that moment on, Mars is no longer made solely from the ingredients of our own star. It carries, in the faintest possible way, the fingerprint of another sun. A dynamical purist might say, but it's just an atom. A philosopher might say, but it's a new branch added to an old story. And they would both be right. The question also plays out in gravity. Every time two objects pass each other in space, they trade a tiny tug, a gravitational nudge that alters their trajectories ever so slightly. That happened here too. Mars, with its modest mass, pulled gently on 3I Atlas as it swept past. Not enough to change the comet's destiny in the immediate sense, but enough that, over tens of thousands of years, its course through the galaxy will be different than it would have been without this encounter. And the same goes the other way. 3I Atlas tugged lightly on Mars, adding a shift so infinitesimal that no instrument could measure it. But gravity keeps receipts. Every nudge, every pull, every whisper of influence adds to the ledger of a planet's long-term motion. On cosmic scales, forever is just the sum of very small nudges, said dynamicist Dr. Karim Yusuf. And in that sense, yes, Mars has changed forever, perhaps only by a fraction of an arc-second. But forever is made of fractions. The deeper question, the one that tends to rise for listeners like you, men who have lived long enough to appreciate nuance, is this. Does any of this matter to us down here on Earth? The answer depends on what you consider important. If you're looking for immediate consequences, storms, quakes, new chemistry forming oceans, then no, nothing like that happened. The event was quiet, gentle, a meeting without fireworks. But if you're looking for what it says about our place in the cosmos, how worlds interact, how star systems exchange material, how the universe stitches its stories together, then yes, it matters deeply. Because what happened near Mars is a reminder that planets are not closed boxes. They are permeable, influenced, connected, and once in a very long while, they are touched by something from another sun. This encounter will not reshape Mars's climate. It will not rewrite its geology, but it has rewritten something else. The idea that planets exist entirely alone in their origins. Now we know they don't. Now we know Mars has been brushed by stardust from another neighborhood. Now we know that chemical stories travel farther than we once believed. So did Mars change forever? Not in the dramatic sense, but in the honest sense, the atomic, gravitational, philosophical sense. Yes, something foreign passed by and left a mark so subtle you cannot see it, but so real you cannot deny it. For a world that has stood unchanged for billions of years, even that is meaningful. Even that is a form of transformation. And if a quiet brush with an interstellar comet can nudge a planet, what can it teach a civilization about its own future? Once the dust settled, literally and figuratively, and the data from Mars finished streaming down, scientists around the world began to see the encounter with 3I Atlas for what it truly was. Not just a scientific opportunity, but a rehearsal, a full-scale, real-time stress test of humanity's ability to detect, predict, coordinate, and respond to something that does not belong to our solar system. No alarms, no danger, no world-ending scenario, but a priceless chance to practice. In the field of planetary defense, practice is everything. Unlike storms or earthquakes, the universe does not give us frequent reminders. Objects from other stars are rare. Close approaches are rarer still. And visitors passing near a planet with orbiters already in place. That's the kind of alignment that feels less like planning and more like the universe handing you a quiet, unexpected drill. Teams quickly recognized that this was an opportunity to test the most important pillars of planetary defense. First, detection. 3I Atlas was spotted, identified as interstellar, and tracked with surprising speed. Not because our systems are perfect, but because enough telescopes happen to be online, pointed at the right regions of sky, with enough analysts awake at their desks that night. Its hyperbolic path was flagged early, and its unusual speed, too fast to be gravitationally bound to the sun, was logged. The detection pipeline worked, but it worked under pressure and with a bit of luck. Second, orbit refinement. Once the possibility of a close Mars flyby was raised, the global community began running the kind of ephemeris updates normally reserved for objects heading toward Earth. Teams practiced the dance, cross-checking observations, tightening uncertainties, recalculating trajectories every few hours. It wasn't frantic, it wasn't fearful, but it was focused. Watching the approach unfold across days and hours gave everyone a chance to rehearse how quickly we can refine a path when the stakes are higher. Third, coordination. Maybe the most important pillar of all. The world didn't have one team watching 3I Atlas. It had dozens. NASA, ESA, CNSA, amateur astronomers, university teams, deep space antenna networks, and orbiters circling Mars like sentinels. This event tested something no simulation can perfectly mimic. Whether scientists divided by politics, time zones, agency rules, and funding constraints could move in sync. And to everyone's relief, they did. They did it even while NASA was under a partial shutdown. They did it even while budgets were frozen and staffing was inconsistent. They did it even as each agency had its own priorities, its own internal pressures, its own bureaucratic limits. That is worth pausing on, because it means that when the universe hands humanity a time-critical puzzle, our species is capable of responding, not flawlessly, not effortlessly, but effectively. Still, everyone involved knows the truth. Part of this success rested on luck. Mars already had 3 orbiters in place, operational, healthy, and flexible enough to be repositioned. If Maven had been down, or if Mars Express had lost a gyro, or if MRO had been in safe mode, much of the data we now treasure simply would not exist. Luck also played into timing. 3I Atlas passed Mars when the red planet was well positioned for Earth-based telescopes, when the deep space network was not overloaded with other missions, when weather cooperated in Chile, Hawaii, and Australia. Had any one of those things broken differently, the story we're telling tonight might be thinner, more speculative, missing key pieces. That is the part planetary defense experts worry about. Not doom, not fear, but dependence on chance. Because next time, the visitor may not pass harmlessly. It may come closer, faster, or on a trajectory that intersects Earth rather than another world. And when that happens, our readiness needs to rely less on lucky alignment and more on preparation. Systems intentionally built to see, respond, and coordinate without depending on which orbiters happen to be active that week. This isn't a warning. It's a marker of growth. Humanity is learning. We are not helpless. Our species is slowly becoming a civilization that can look outward, truly outward, at the vastness of space and recognize that what happens out there matters to what happens down here. The encounter between Mars and 3I Atlas didn't threaten any world, but it revealed, gently and quietly, how far we've come and how far we still need to go. Detecting interstellar objects early, understanding their chemistry, tracking their trajectories with precision, coordinating across borders and budgets, sharing data without hesitation, keeping spacecraft healthy enough to act when the universe hands us a narrow window. Every harmless visitor is a rehearsal for the one we can't afford to ignore, said Dr. Rachel Moore, a planetary defense officer who has spent her career thinking about scenarios most people dismiss until they appear in headlines. And she's right. This wasn't just a scientific event. It was a step in our species' ongoing education. A quiet lesson passed from one sunless wanderer to a planet full of people learning to pay attention. And when the rehearsal ends and the data is saved, what's left is something quieter, saying goodbye. By the time the last bits of data settled onto servers across Earth, 3I Atlas was already slipping away, quietly, steadily, without ceremony. The same object that had set off months of calculations, sleepless nights, crossed emails, and frantic scheduling began to shrink in every telescope's field of view. Its bright coma, once swollen by sunlight and heat, started to collapse. The jets of gas that once streamed from its sunlit surface faded into stillness. What had been a breathing, glowing visitor became, once again, what it had been for most of its life. A cold, dark shard of ice and rock adrift between the stars. Out near the orbit of Mars, the warmth of the sun weakens quickly. Day by day, 3I Atlas shed less gas. Its tail shortened, its coma dimmed, its activity slowed until it resembled nothing more than a muted smudge of reflected sunlight, fainter each week, then each day, then each hour. The last images from the ground made it look almost shy, receding into the background glow of distant stars. And soon, even the brightest telescopes needed longer exposures just to catch a hint of it. The universe doesn't do farewells in human terms. There are no fireworks, no fanfare, no final wave. Just distance, just dimming, just a gradual letting go. As 3I Atlas retreated from the inner solar system, its path arced outward into a trajectory that would eventually, very slowly, carry it toward the region of sky we know as Cygnus, the Swan. It will not reach any star there in our lifetimes, or in the lifetimes of our distant descendants. Tens of thousands of years will pass before it comes anywhere close to another sun. Maybe longer. Maybe it will drift in silence until the galaxy itself evolves into a new shape. But its direction is set. Its fate is written into its momentum. A faint, ancient traveler gliding into darkness once again. For the scientific teams who had spent months tracking it, there was a strange mix of emotions once it faded beyond reach. Relief, of course. After all the tension, the deadlines, the orbit updates, the coordination across agencies, there was comfort in knowing the encounter was complete. But there was also something else, a hollow quiet, the emotional equivalent of standing on a doorstep after a long-awaited guest has left. Some scientists joked about it. Some wrote short, almost sentimental notes in their internal logs. A few sent emails that read more like farewell letters than technical reports. Because even though 3i Atlas was never ours, it had occupied our collective attention for long enough that its departure left a small but noticeable space behind. The data it left, however, that will not fade. That is its time capsule. Terabytes of spectra, images, graphs, timing logs, and atmospheric measurements now live quietly in storage arrays around the world. They're backed up in mirrored servers, mirrored again on cloud systems, copied onto research drives, and archived in databases that future scientists will one day browse through. Maybe years from now, a graduate student running a late-night analysis will click on a file labeled Atlas Mars Flyby 2025 and see something new hiding in the noise. Maybe someone will use these measurements to compare with another future interstellar object. Maybe in 2125, a researcher will give a talk referencing the historic hydrogen spike from the first well-documented interstellar comet encounter. Everything we learned from 3i Atlas has become a gift to people not yet born. A message in a bottle tossed into time. And what about you? Lying here now, in the dark, listening to this story unfold. You live on a world that circles a warm star, a world wrapped in oceans and forests and cities, glowing faintly with human activity. Tonight, you are listening from a small corner of that world as the universe continues its slow, patient motion. And somewhere far, far beyond the reach of your eyes, the visitor who brushed past Mars is shrinking into obscurity, carrying on with its own ancient journey. It passed near the neighborhood of your home, just close enough for your species to notice, to take measurements, to marvel at the chemistry it carried, to wonder how many visitors like it have come and gone before anyone was watching. No catastrophe, no impact, no threat, just a quiet reminder that even in a vast and indifferent universe, encounters can be gentle. The story of 3i Atlas and Mars will not end up in most newspapers. It will not rewrite school textbooks, but it will sit quietly in the scientific record, a soft punctuation mark in the long biography of our solar system. And for you, listening now, it offers something simpler, a sense of proportion, a sense of calm, the reassurance that the universe is wide enough to hold mysteries without holding malice, a reminder that not every cosmic event demands fear. Some simply invite reflection. Sometimes, the most important thing a visitor does is simply remind us that the universe is bigger than our fears, said cosmologist Dr. Elise Novak. As 3i Atlas drifts toward Cygnus, fading deeper into night, you're free to let your thoughts drift with it. Let them stretch outward to the quiet distances between stars. Let them soften. Let them rest. Because for now, the visitor is gone. Mars is quiet. Earth is still turning. You can close your eyes. The universe will keep watch.